All right, last example. Eigenvectors and eigenvalues are certainly not limited to 2 by 2 matrices. In fact, n by n matrices are far more interesting and more common. So when we look at a 3 by 3 matrix, for example, we still have, in principle, as many as 3 eigenvalues, as many as 3 eigenvectors. Let's just take a look at this thing and try to figure out what its eigenvectors are, what its eigenvalues are. First, let's look for those eigenvalues. So again, we're going to use this a minus lambda I. Now in this case, this I is a 3 by 3 I, and this is going to yield 3 minus lambda, 0, 0, 0, 3 minus lambda, 0, 0, minus 1, 2 minus lambda. 3 by 3 determinants are a little bit more complicated, but I chose this matrix in large part because it's pretty easy to write down the determinant. The determinant is just 3 minus lambda quantity squared times 2 minus lambda. And this has a couple of roots. Those two roots are 2 and 3, where lambda is equal to 2 with algebraic multiplicity equal to 1, and lambda is equal to 3 with algebraic multiplicity equal to 2. So the root 3 is a double root, the root 2 is a single root. Now let's take a look at those eigenvectors. First, let's look at that eigenvector with lambda equal to 2. Let's look at this whole thing as a minus lambda I. Let's look at that with lambda equal to 2. We've got 1, 1, 0. We got our same minus 1 and our 0 and our 0 and our 0 and 0 and 0. We have this multiplied by x1, x2, x3. And if we think about this as a system of equations, again, just doing the same thing in 3 dimensions that we did in 2 dimensions, this is 0. Well, what we get is we get x1 is equal to 0 from the first line. We get x2 is equal to 0 from the second line. And we get minus x2 is equal to 0. So x2 is really 0. It's a lot of 0. But it doesn't say anything about x3. So then this vector, let's call this v1. It's 0 here, it's 0 here, and it's whatever you want here. So I'm boring, I'll put a 1 there. That vector, or any scalar multiple of it, has an eigenvalue of 2. But now let's go back and let's think about this eigenvalue of 3. So let's erase this stuff. And here we're going to use 3. So the only thing that changes is the diagonal. We get 0 here, we get 0 here, and we get a minus 1 there. Now, these first two equations then, as we think about these as systems of equations, the first one says 0 plus 0 plus 0 is equal to 0. True, but uninteresting. The second one also says 0 is equal to 0. So that's not a whole bunch of use to us. The last one says that minus x2 minus x3 is equal to 0, or in other words, x2 is equal to minus x3, or x3 is equal to minus x2, however you want to think about it. Now, here you might say, well, are there one vector for which that is true, or are there many vectors for which that's true? This could be a defective matrix, or it could be a complete matrix. We just need to know how many vectors there are. The algebraic multiplicity is 2, so we think there might be as many as 2 independent vectors, but we don't know. So let's try to find one. Well, let's talk about the vector 0, 1, minus 1. That's a vector for which the second element is the negation of the third element. Certainly satisfies the equation. Let's call that v2. And then let's ask ourselves, can we find another vector which also satisfies it, but isn't a linear copy of that? And I'll say, yeah, sure we can. Let's look, for example, at v3 is equal to 1, 0, 0. Right? There's no constraint on x1. There's no constraint on that first element. So how about that one? It doesn't really matter what you choose in x1. You can have a non-zero element here. That would be fine as long as these two things are not quite the same. You'll discover that they are linearly independent. So here we have 2 linearly independent vectors, and we have therefore a geometric multiplicity of 2 on that eigenvalue, which is equal to its algebraic multiplicity. This is also a complete matrix. For those of you who care about such things, note that any vector on a plane, that plane being y is equal to minus z, any vector on that plane is scaled by 3, and the direction of it is left alone. That's what's meant by an eigenplane. Pick a vector on that plane, and it's treated as an eigenvector.